The morning of November 12, 1942, arrived like any other day at the Permanente Metals Corporation facility in Richmond, California. Workers streamed through the gates at 7:30, carrying lunch pails and thermoses filled with coffee. The air smelled of metal and oil. Men pulled on heavy gloves and adjusted their welding masks. In the first construction bay, sparks began to fly as torches cut into steel plate. This was the beginning of Hull for 44, and nobody that morning realized they were about to participate in something that would alter the course of the war. Shipyards dotted both American coasts by this point in the conflict. Vessels were under construction everywhere. But something different was happening in Richmond. The owner of the facility, industrialist Henry Kaiser, had made a wager, he claimed. His workforce could construct a complete 10,000-ton cargo vessel in less than 5 days. Not just a hull, not just launching an unfinished frame into the water. He meant a fully operational, seaworthy merchant ship ready to carry cargo across an ocean. Everything installed, engines running, electrical systems functioning, navigation equipment in place, paint applied, ready to sail immediately across the Atlantic Ocean, in the concrete submarine pens along the occupied French coastline, and in the naval offices of Berlin. German strategists would have considered such a claim absurd. Their entire approach to winning the war at sea rested on straightforward arithmetic. German submarines could sink Allied merchant vessels faster than those ships could be replaced. If this remained true, Britain would eventually run out of supplies. The Soviet Union would collapse without American aid. Any invasion of continental Europe would become impossible. The numbers appeared to support this strategy completely. Traditional shipbuilding required 6 months to a year for a single merchant vessel. A submarine could send that ship to the bottom in minutes. German naval intelligence had conducted thorough research. They understood British shipbuilding capacity in detail. They had analyzed American industrial output from the previous World War. They had studied construction timelines for conventional merchant ships built using established methods. Their analysts produced comprehensive reports demonstrating that even under maximum effort, the Allied powers could not replace tonnage faster than German submarines destroyed it. The mathematics were clear. The logic was sound. Germany would win the war of tonnage. What German planners did not know, what they could not have anticipated, was that Americans were not building ships using traditional methods. They were applying the same techniques Henry Ford had used to mass-produce automobiles. Assembly line production, prefabricated sections manufactured separately and assembled rapidly. Mass production principles applied to vessels that had always been custom-built one at a time. And they were constructing these ships at a pace that would have seemed like pure fantasy to anyone trained in conventional naval architecture. The vessel that would emerge from Hull 444 would be named SS Robert E. Peary, after the Arctic explorer. Its construction would be filmed and documented extensively. It would serve as a propaganda tool and a morale booster, but more importantly, it would demonstrate what American industrial capacity could accomplish when fully mobilized. It would represent the moment when German calculations broke down, when the fundamental assumptions underlying their Atlantic strategy proved false, when the arithmetic that said they were winning would itself to be based on outdated ideas about how quickly a modern industrial democracy could produce weapons of war. The welders working in Bay No. 1 that November morning did not think they were making history. They understood they had work to do. There was a war happening. Ships were desperately needed. They knew about bonus payments being offered for speed. They knew supervisors were watching the clock closely. What they did not understand was that their work over the next 4 days would help answer one of the central questions of the entire war. Could industrial production defeat military strategy? Could factories win battles that navies could not? The struggle for control of the Atlantic sea lanes had begun the moment Britain declared war on Germany in September 1939. German submarines operating from bases in Germany and later from occupied France, hunted Allied merchant convoys. These convoys carried food, fuel, equipment, and raw materials to Britain. The strategic concept possessed elegant simplicity. Britain was an island nation, importing most of its food, and nearly all of its petroleum. Sever those supply lines and Britain would face surrender, regardless of how many soldiers it could field or how determined its population remained. Admiral Carl Dönitz commanded the submarine fleet. He had calculated exactly how much tonnage needed to be destroyed each month to achieve strategic victory. His figure was 700,000 gross register tons monthly. Maintain that level of destruction consistently, and British imports would fall below the minimum necessary to sustain the war effort. Britain would face a choice between starvation and capitulation. The arithmetic was brutal but clear. For much of 1940 and 1941, the submarines were winning. German underwater boats hunted in groups called Wolf packs. 8 to 20 submarines would coordinate their attacks on convoys. A single boat would shadow a convoy, transmitting its position to headquarters by radio. Other submarines would converge on that location. Then at night, they would strike simultaneously from multiple directions. Merchant ships, slow and unarmed, possessed little defense. Torpedoes struck hulls, ships broke apart. Men entered the freezing Atlantic water, oil spread across the surface and ignited. The submarines would slip away before escort vessels could mount effective counterattacks. The statistics told a devastating story. In 1940, German submarines sank more than 1,000 Allied merchant ships. In 1941, they destroyed over 800 more. Tankers carrying petroleum from American refineries to British ports burned and sank. Freighters loaded with food, aircraft components, ammunition, and vehicles disappeared beneath the waves. Each sinking represented not merely lost cargo, but lost crews. Men died from hypothermia in lifeboats or went down with their ships when torpedoes struck without warning. British shipyards worked frantically to replace losses, but could not maintain pace. Traditional shipbuilding was intensely time-consuming, requiring skilled craftsmen. A merchant ship was constructed on a slipway with each plate riveted individually into position. Frames were built piece by piece. Engines were installed through complex lifting operations. Systems were hand-fitted throughout the vessel. The entire process from keel laying to launch consumed 8 to 12 months for an experienced shipyard operating at full capacity. Britain possessed experienced yards, but insufficient numbers of them, insufficient workers, and insufficient steel. The United States, still officially neutral, watched with mounting concern. President Franklin Roosevelt understood that British survival was critical to American security. If Britain fell, America would face a hostile German-dominated Europe with no allies and no forward bases. However, American neutrality laws restricted direct military aid. The solution emerged as the Lend-Lease program announced in March 1941, which permitted the United States to provide war materials to Britain without requiring immediate payment. Ships, aircraft, tanks, and food would flow to Britain as long as Britain could maintain its sea lanes, but Lend-Lease only functioned if supplies could actually reach Britain. That meant ships, enormous numbers of ships, more ships than anyone had ever constructed before, ships built faster than submarines could sink them. Ships built in such quantities that losing them to torpedoes became an acceptable course rather than a strategic disaster. The question was whether such achievement was even possible, whether industrial techniques that had revolutionized automobile production could be applied to shipbuilding, whether mass production could defeat submarine warfare. The man who believed it possible was Henry John Kaiser, an industrialist who had never built a ship in his entire life. Kaiser had built his fortune in construction, creating roads, bridges, and dams across the American West. He had participated in the consortium that built Hoover Dam, one of the largest engineering projects in American history. He understood large-scale industrial organization and mass production techniques. He knew how to manage thousands of workers on complex projects. What he did not understand, and what would prove his greatest advantage, was traditional shipbuilding. Traditional shipbuilders were craftsmen. They had learned their trade through apprenticeships lasting years. They knew ship design intimately, understood stresses on hulls, and took pride in building vessels that would last decades. Each ship was in some sense unique, adjusted during construction to account for variations in materials and slight differences in design. This approach produced excellent ships, but produced them slowly. Kaiser examined this process and saw inefficiency everywhere. He saw skilled workers performing repetitive tasks that could be standardized. He saw construction happening sequentially when it could occur in parallel. He saw craftsmanship where he needed mass production. The British had already begun moving in this direction with their emergency shipbuilding program. British yards had developed designs for simple standardized cargo ships that could be built more quickly than traditional vessels. These ships sacrificed elegance and longevity for speed of construction. They were welded rather than riveted, saving time and weight. They used prefabricated sections where possible. They employed simpler propulsion systems. The British called them Empire ships, and they served adequately, although never built in quantities needed. When the United States entered the war in December 1941 after the Japanese attack on Pearl Harbor, the shipping situation became critical. America now needed to supply not just Britain, but also the Soviet Union through dangerous Arctic convoys. American forces deploying to Europe, North Africa, and the Pacific needed transport. The existing merchant fleet, already strained, was completely inadequate. The United States Maritime Commission, responsible for coordinating merchant ship construction, approached Kaiser and other industrialists with a proposal: build merchant ships using mass production techniques, build them in new yards constructed specifically for this purpose, build them in quantities that seemed impossible. The design they would construct was called the Liberty ship, based on a British design, but modified for American production. The Liberty was not beautiful. It was a simple, boxy cargo vessel, 441 feet long with a beam of 57 feet. It displaced 14,450 tons when fully loaded. It could carry 10,000 tons of cargo in 5 holds. It was powered by a reciprocating steam engine, an old-fashioned design chosen because it was easy to manufacture and maintain. The engine produced 2,500 horsepower, giving the ship a top speed of 11 knots, roughly 12.5 miles per hour. It was slow, ungainly, and utilitarian, but it could be built quickly. The design used welding throughout rather than riveting, reducing construction time by 40%. It employed prefabrication extensively. Entire hull sections could be built in one part of the yard while the keel was being laid elsewhere, then lifted into place by massive cranes. The engine, the deck houses, even the masts and booms were standardized components that could be manufactured separately and installed as complete units. Everything about the Liberty ship was designed for mass production. Kaiser took this concept further than anyone thought possible. At his Richmond yard and at other facilities he built along the West Coast, he hired workers with no shipbuilding experience, farmers, teachers, women who had never worked in heavy industry, men too old for military service. He trained them in specific tasks rather than teaching them the complete craft of shipbuilding. One worker would weld vertical seams, another would weld horizontal seams, a third would install electrical conduits, a fourth would paint. Each person became expert in their narrow specialty, and the assembly line moved forward. The Richmond shipyard operated on a scale that defied traditional understanding. The facility covered over 600 acres of land that had been tidal mudflats 18 months earlier. Kaiser's company had driven thousands of pilings into soft ground, poured concrete foundations, erected steel frameworks for assembly buildings, and installed massive cranes capable of lifting entire ship sections, weighing hundreds of tons, by the time Hull 444 was being laid. The yard employed over 90,000 workers across multiple shifts. The facility operated 24 hours daily, 7 days weekly. Lights blazed through the night. Welding torches never stopped. The sound of metal on metal, the hiss of cutting torches, the clang of hammers, and the rumble of cranes created a constant industrial symphony audible for miles. The workers themselves came from everywhere. Many were women, drawn by wages higher than anything available in traditional female employment. They worked as welders, crane operators, electricians, and pipe fitters. They wore work pants and safety goggles and learned to handle equipment that weighed more than they did. Some had been teachers or secretaries before the war. Others had been farm wives or shop clerks. The shipyards trained them in weeks for jobs that would have required years of apprenticeship, traditional shipbuilding. One woman who had been a seamstress in Oakland learned to weld vertical seams on hull plates. She could lay a bead that passed inspection on her third day of training. Within 2 months, she was teaching others. The prefabrication system was the key to the entire operation. Rather than building a ship from the keel upward in sequential stages, Kaiser's yards built ships in sections, simultaneously dotting one part of the yard. Workers assembled the bow section complete with all interior framing, deck plates, and structural supports. In another area, crews built the stern section, with engine mounts and propeller shaft housing already installed. Midship sections, each 100 feet long and 3 stories tall, were constructed on separate assembly platforms. Each section was complete with wiring conduits, piping runs, ventilation ducts, and structural reinforcements before it ever reached the slipway, the double bottom. The internal hull structure that provided strength and housed ballast tanks was assembled as complete units. Workers would build a double-bottom section flat on the ground, where they could work standing upright rather than crawling in confined spaces. Once complete, cranes would lift the entire section and lower it into position on the growing hull. What had taken weeks of cramped, difficult labor in traditional shipbuilding now took days of efficient work in comfortable conditions. The same principle applied to deck houses, structures above the main deck containing crew quarters, the bridge, and other facilities. These were built as complete units in manufacturing shops with all interior walls, doors, windows, electrical fixtures, and plumbing already installed. When the time came, a crane would lift the entire deckhouse, weighing 30 or 40 tons, and set it in place on the deck. Workers would then weld it down and connect utilities. A process that traditionally took months happened in hours. The welding itself represented a revolution in ship construction. Traditional ships were riveted, with each rivet requiring a team of 3 or 4 workers. One person heated the rivet to red heat in a portable forge. Another positioned it in the pre-drilled hole. A third hammered the head into shape, while a fourth held a bucking bar on the opposite side. The process was loud, hot, dangerous, and time-consuming. A good riveting crew could set perhaps 200 rivets in a shift. A single Liberty ship wired over 1 million rivets using traditional construction methods. Welding replaced all of that. An electric arc welding machine operated by a single person could join steel plates continuously along their entire length. The welds were stronger than rivets, created watertight seams without caulking, and weighed less because no additional material was needed. A welder could complete in 1 day what would have taken a riveting crew a week. The Liberty ship design called for approximately 3,000 individual welds of various lengths. With multiple welders working simultaneously on different sections, welding could be completed in a fraction of the time traditional riveting required. Kaiser's yards employed thousands of welders, many of them women, working around the clock in shifts. The speed of construction created its own challenges. Quality control became critical. Inspectors moved through the yard constantly, checking welds with radiographic equipment and magnetic particle testing. Any defect meant stopping work on that section until repairs were made. The Maritime Commission maintained strict standards. Ships had to be seaworthy, had to pass sea trials, had to be safe for the crews who would sail them into combat zones. Speed could not come at the expense of basic structural integrity. The inspection process slowed construction somewhat, but ensured that ships would not simply fall apart at sea. German naval intelligence watched American shipbuilding with growing concern, but their analysis remained rooted in traditional assumptions. Reports reached Berlin, describing new shipyards being constructed along American coasts. Aerial reconnaissance photographs taken by long-range aircraft showed the Richmond facility and similar yards in Maine, Maryland, and along the Gulf Coast. German analysts examined these images and calculated construction rates based on their understanding of shipbuilding. They counted slipways, the inclined structures where ships were built before launching. Richmond had 12 slipways. Traditional analysis suggested each slipway could produce perhaps 4 ships annually. Assuming a construction time of 3 months per ship, 12 slipways meant 48 ships annually from Richmond alone. Even if Americans built 10 such facilities, that would total fewer than 500 ships per year. Substantial certainly, but not overwhelming. Submarines could sink 500 ships if they maintain their operational tempo from 1941. What German analysts missed was that Americans were not using traditional construction schedules. The prefabrication system meant most of the ship was built before it ever occupied a slipway. The slipway itself was used only for final assembly and launching, a process consuming weeks rather than months. A slipway that would traditionally produce 4 ships annually was now producing 12 or 15. And Americans were building not 10 yards, but dozens scattered across both coasts, each employing tens of thousands of workers. The scale of the American effort was difficult to comprehend even for those who knew the numbers. The Maritime Commission had authorized construction of 200 Liberty ships in the initial production run. This was soon increased to 300, then 600, then more. By mid-1942, the target exceeded 1,000 ships. By 1943, the program would expand to over 2,500 vessels. No nation had ever attempted shipbuilding on this scale. No nation possessed the industrial capacity, raw materials, workforce, or organizational systems to build that many ships. Steel mills in Pennsylvania and Ohio rolled plate steel around the clock. Steel was shipped by rail to shipyards in massive flat cars, each carrying dozens of tons of plate. Pipe manufacturers produced thousands of miles of piping for steam lines, water lines, fuel lines, and ventilation systems. Engine manufacturers built reciprocating steam engines by the hundreds. The engines were not sophisticated, but they were reliable and could be manufactured quickly using existing machine tools and experienced workers. Electrical equipment manufacturers produced generators, switchboards, wiring, and lighting fixtures in standardized designs, installable in any Liberty ship. The logistics of moving all these materials and components to shipyards required its own organizational miracle. Railroads, already strained by military traffic and general wartime industrial production increases, had to schedule additional freight trains to carry ship components. Trucks moved materials from rail yards to shipyards. Warehouses stored materials in organized systems, allowing workers to find exactly what they needed when they needed it. Inventory control, a concept still relatively new in manufacturing, became essential. Running out of a critical component could shut down an entire section of the yard. The human cost of this industrial mobilization was substantial but manageable. Shipyard work was dangerous. Workers fell from heights, were crushed by moving equipment, were burned by welding slag, or injured in countless other ways. Safety programs reduced but could not eliminate these hazards. Yards employed nurses and doctors who treated injuries on site. Serious cases were transported to hospitals that had established special wards for shipyard workers. Despite the dangers, workers kept coming because wages were good, because the work felt important, and because everyone understood the war could not be won without ships. The workers themselves developed a culture, an identity around their labor. They called themselves shipyard men and shipyard women with pride. They competed informally between shifts to see who could complete work faster or more efficiently. They took pride in the ships they built, attending launches when their ship was completed, and following news reports about vessels they had worked on. When a Liberty ship survived a torpedo attack and made it to port, workers who had built that ship felt personal satisfaction. When a ship was sunk, they felt the loss. Hull 444 began as a series of steel plates laid on keel blocks in Bay No. 1 at 7:30 on the morning of November 12, 1942. By noon, the keel structure was complete, 300 feet of welded steel running the length of the slipway. Workers swarmed over the structure, positioning frames, welding supports, and laying deck plates. Overhead cranes swung prefabricated sections into position. Welders moved along seams, their torches leaving glowing trails of molten metal that cooled into permanent bonds. By the end of the first day, the double bottom was in place. By the morning of the second day, hull sides were rising. Prefabricated sections, each as large as a two-story house, were lifted by crane and positioned against frames. Welders secured them. More sections followed. The hull took shape with startling speed, growing taller and longer with each passing hour. Workers inside the hull installed structural supports, laid piping, and ran electrical conduits. Work happened simultaneously at dozens of locations throughout the growing ship. On the third day, the deck was laid. Steel plates were positioned and welded to create the main deck surface. Cargo hatch openings were framed and reinforced. Deck houses arrived by crane, complete units with windows already glazed and interiors painted. They were lowered onto the deck, positioned precisely, and welded into place. Inside, other workers connected electrical systems and plumbing lines. The bridge structure, the highest point on the ship where captain and officers would navigate, was installed complete with all instruments and controls. The engine arrived on the fourth day, a reciprocating steam engine weighing over 140 tons. It came on a special railway car, was transferred to a shipyard crane, and lifted over the side of the growing vessel. Workers guided it into the engine room through an opening that would later be covered by deck plates. The engine settled onto its mounts with a sound like thunder. Workers immediately began connecting steam lines, fuel lines, and the propeller shaft. The boilers followed, to large cylindrical vessels that would generate steam to power the engine. They were also installed as complete units docked by the morning of the fifth day. November 17th, the SS Robert E. Peary was complete. Workers had painted the hull grey and black, standard merchant marine colours. They had installed masts and booms used for loading and unloading cargo. They had stocked the galley with food, filled fuel tanks with oil, and loaded crew quarters with bedding and supplies. Maritime Commission inspectors walked through the ship checking systems. Everything worked. The engine turned when steam was applied. Electrical systems functioned. Pumps moved water. The ship was ready for launch at 2 in the afternoon on November 17th, 4 days and 15.5 hours after the keel had been laid. The SS Robert E. Peary slid down the slipway into San Francisco Bay. Workers cheered. Horns sounded across the shipyard. Newsreel cameras captured the moment. Henry Kaiser stood watching, knowing his workers had just proven something that would change the war. They had built a complete ocean-going merchant ship. In less time than it took to sail one across the Atlantic, the news reached Washington within hours. Maritime Commission officials, who had watched construction with a mixture of hope and skepticism, now had proof that mass production shipbuilding worked. The news reached London, where British officials struggled to understand how a ship had been built faster than some Royal Navy vessels took to refuel and resupply. And the news reached Berlin, carried in intelligence reports that German naval staff read with growing disbelief. The mathematics had changed. If Americans could build a ship in 5 days, they could build 70 ships per year from a single slipway. Richmond had 12 slipways. That was 840 ships per year from one yard alone. Americans had dozens of yards. The calculation that had seemed so solid, that submarines could sink ships faster than they could be built, was revealed as dangerously wrong. Americans were not building ships at peacetime rates. They were not even building them at emergency rates comparable to British production. They were building them at industrial mass production rates that had no historical precedent. German submarine commanders operating in the Atlantic began reporting strange experiences. They would sink a merchant ship, documenting its tonnage for headquarters. Weeks later, they would encounter another ship with an identical profile, same dimensions, same appearance, even the same general cargo capacity. At first, they assumed these were sister ships from the same builder, but the frequency of encounters suggested something else. The ships were not merely similar. They were identical, mass-produced, built from the same plans, with the same components, in the same configuration. One submarine commander reported sinking 5 ships over 2 months that were so alike he initially thought his patrol reports contained errors. They were not errors. They were Liberty ships, turned out by American yards, like automobiles from an assembly line. The SS Robert E. Peary sailed from San Francisco Bay on December 2, 1942, bound for the Atlantic with a cargo of war materials. The ship made the voyage through the Panama Canal and across to Britain without incident, delivering its cargo to ports that desperately needed resupply. It returned to the United States, loaded another cargo, and sailed again. Over the next 3 years, the Peary would complete 5 round-trip voyages across the Atlantic, carrying thousands of tons of supplies to support the war effort. The ship survived the war intact, one of the fortunate Liberty ships that never encountered a submarine or struck a mine. But the Peary's importance was never its individual service record. It was proof of concept. After November 17, 1942, no one could claim that building ships in a matter of days was impossible. Kaiser's yards and others across the country shifted into maximum production. Average construction time for a Liberty ship went from initial estimates of several months to approximately 42 days from keel laying to launch. Some yards achieved even faster times. The record set by the Peary stood, but dozens of ships were completed in 7 to 10 days. Hundreds were built in under 30 days. The production numbers became staggering. In 1942, American yards launched 346 Liberty ships. In 1943, they launched over 1,800. In 1944, another 1,000 ships joined the merchant fleet. By war's end, American shipyards had constructed 2,710 Liberty ships, along with hundreds of other merchant vessel types, including faster Victory ships, tankers, and specialized cargo vessels. Total tonnage produced exceeded 27 million gross register tons. German submarine commanders watched this fleet grow with increasing desperation. Their patrol reports documented the problem in stark terms. One commander operating off the American East Coast in early 1943 reported observing a continuous stream of merchant vessels heading for convoy assembly points. He counted more than 30 ships in a single day, far more than his boat could possibly engage. Another commander hunting in mid-Atlantic convoy routes reported that convoys themselves had grown larger. Where a typical convoy in 1941 might consist of 30 to 40 ships, by 1943 convoys often numbered 60 to 80 vessels, with escort forces that made attack suicidal. The strategic mathematics that Admiral Dunitz had relied upon collapsed entirely. His target of 700,000 tons sunk per month had been based on the assumption that Allies could not replace losses faster than submarines could inflict them. But American production alone was launching more than 1 million tons of new shipping every month by 1943. Even accounting for British and Canadian production, Allies were adding tonnage to their merchant fleet faster than Germans could sink it. The tonnage war, the fundamental strategic goal of the submarine campaign, was lost. Dunitz refused to accept this reality 4 months He ordered more submarines built, more patrols sent out, more aggressive tactics employed. German shipyards constructed new submarines at remarkable rates, completing over 200 boats in 1943 alone. But submarines took months to build, required trained crews, and consumed scarce resources that German industry desperately needed for other purposes. Each submarine represented steel that could have built tanks, skilled workers who could have produced aircraft, and diesel fuel that ground forces needed. The resource allocation made less sense with each passing month, as it became clear the submarine campaign could not achieve its strategic objectives. The human cost mounted on both sides. Submarine crews, young men who had volunteered for what they believed was the elite service of the Navy, died in their steel coffins as Allied anti-submarine warfare improved. Of approximately 40,000 German submariners who served during the war, over 30,000 were killed. The casualty rate, 75%, was the highest of any branch of any military service in the entire war. These men died knowing their sacrifice was achieving nothing, that every merchant ship they sank was replaced by two more, that the Atlantic was becoming an Allied highway rather than a German barrier. Merchant sailors on the Allied side paid their own terrible price. Over 30,000 British merchant seamen died during the war, killed when their ships were torpedoed, bombed, or mined. American merchant marine casualties exceeded 9,000 dead. These men were civilians, not military personnel. Although they served in combat zones and faced combat dangers, they sailed knowing submarines hunted them, that a torpedo could strike without warning, that survival in cold Atlantic water was measured in minutes. They sailed anyway because supplies had to get through. The Liberty ships themselves proved adequate vessels, although far from perfect. They served their purpose of moving cargo across oceans in massive quantities, but they had significant limitations. The reciprocating steam engines were reliable but slow, limiting ships to about 11 knots in calm seas and less in rough weather. This made them vulnerable to submarines, which could travel faster on the surface and maneuver more quickly. The welded construction, while faster than riveting, created problems in cold water. Some Liberty ships developed cracks in their hulls when sailing in North Atlantic winter conditions. A few broke apart catastrophically when cracks propagated through continuous weld seams rather than stopping at riveted joints. The most famous structural failure was SS Schenectady, which broke completely in half while docked in calm water in Portland, Oregon in January 1943. The ship had been in service less than 2 months. Investigators found that welds had become brittle in cold temperatures, and that stress concentrations at hatch corners had initiated cracks that propagated catastrophically. The incident led to design modifications. Engineers added crack arresters, steel straps that would stop crack propagation. They modified hatch corner designs to reduce stress concentrations. They improved welding procedures and inspection protocols. These changes reduced, but did not eliminate structural problems that plagued some Liberty ships throughout their service lives. Despite these issues, Liberty ships succeeded in their primary mission. They moved cargo in quantities no previous merchant fleet had ever achieved. Convoys arriving in Britain in 1944 might unload more supplies in a week than had arrived in an entire month during 1941. The Soviet Union, receiving supplies through both Arctic convoys and the longer route through Iran, obtained American trucks, aircraft, food, and raw materials that kept its war effort functioning. The invasions of North Africa, Sicily, Italy, and eventually Normandy all depended on logistics enabled by the mass-produced merchant fleet. The invasion of Normandy in June 1944 had more than 5,000 vessels of all types. Among them were hundreds of Liberty ships carrying fuel, ammunition, food, vehicles, and equipment needed to support Allied armies in France. Over following months, as those armies fought across France and into Germany, a continuous stream of supplies flowed across the Atlantic and through French ports. Liberty ships built in American yards by workers who would never see combat, enabled the fighting effectiveness of every Allied soldier in Europe. The Pacific War created equally enormous logistical demands. American forces island hopping across the Pacific needed supplies transported over distances that dwarfed Atlantic routes. From American West Coast ports to forward bases in New Guinea or the Philippines might be 7,000 miles. Every gallon of fuel, every round of ammunition, every ration, every spare part had to travel that distance by ship. Liberty ships and their faster successors, Victory ships, made this possible. They created the logistics network that allowed American forces to advance across the Pacific while maintaining offensive operations in Europe. Simultaneously, Japanese military leaders, watching American logistics in the Pacific, experienced the same growing horror German commanders felt in the Atlantic. They recognized they faced an enemy whose industrial capacity was simply incomprehensible by Japanese standards. Japan had built approximately 600 merchant ships of all types during the war years. American submarines and aircraft sank over 2,000 Japanese merchant vessels, destroying Japan's ability to move resources from conquered territories to home islands. The mathematics worked exactly opposite to how Germans had hoped in the Atlantic. Japan could not build ships faster than America could sink them, and Japan could not sink American ships faster than American yards could build them. Workers at Richmond and other shipyards read about the war in newspapers and heard about it on radio broadcasts. They learned about the Normandy invasion and liberation of France. They heard about American